Hi there, I am Veronique Florec from the University of Western Australia. Welcome to this course on the economics of natural hazards. I have created this video series for anyone in the natural hazards and emergency management sectors that is interested in learning how we apply economic analysis to the management of natural hazards. This project is funded by the Bushfire and Natural Hazards Cooperative Research Centre. Welcome to the 8th video in the series. In this video, we will have a look at how we compare the cost and the benefits of mitigation options. By the end of this video, you will know what to include in the cost of mitigation, what we need to do to be able to compare the cost and benefits of mitigation, and how we think about timeframes for an economic analysis. You will also learn about discounting and the implications of using different discount rates. So far, we have talked about the levels of losses for different scenarios and how we estimate the benefits of mitigation scenarios compared to the counterfactual. We haven't talked yet about timeframes for the analysis, discount rates, and present values. I have purposefully not talked about that yet so that we can take it step by step and introduce one economic principle at a time. Each video introduces a new concept and builds on the knowledge you have gained in previous videos. So by the end of this series, you will have the full picture and a good understanding of all the principles we applied in economic analysis of mitigation, why they're important and how they relate to each other. To discuss the cost of mitigation, I will continue using the example I've used in previous videos. But remember, the same principles can be applied to other natural hazards. In our example, we're looking at two options to mitigate flood impacts in a catchment. Option A involved the construction of a dam in the upper section of the creek. And option B involved upgrading the creek capacity of the creek. We estimated the benefits of implementing option A or option B compared to a baseline scenario of doing nothing. The average annual benefits of option A were $908,050 and option B $737,900. So the average annual benefits of option A are higher than the benefits of option B. Now let's have a look at the cost of building a dam and the cost of upgrading the capacity of the creek. Remember, this is only a hypothetical example, so the cost and benefits presented here do not necessarily represent reality, and were created for the only purpose of explaining the different economic concepts relevant to this course. So they might be very different from the real cost and benefits of flood mitigation. Okay, so let's say that the cost of option A, of building the dam, is $5 million, and the cost of option B, upgrading the creek, is $1.8 million. Also, the dam requires an expenditure of $35,000 for maintenance each year after it is completed, and the creek upgrades require $5,000 on maintenance per year after completion. Both options require 3 years to be completed. So what do we include in the cost? We include all the materials and all the labor required to build the dam or the creek upgrades, as well as any administrative costs, planning cost, compliance cost, and the cost of engaging with the local community. We will basically include any expenditure that is needed in order to put the mitigation option in place and to keep it going, whether the expenditure relates more to the operational side of things or the administrative or planning side of things. Where possible and when the data is available, we will also include in the cost any adverse impacts of implementing the mitigation option. The same will apply to mitigation options for other natural hazards. For example, for prescribed burning, we will include the cost of all the resources needed to conduct the burn, such as fire trucks, planes if they are used, and operational personnel, as well as all administrative costs, planning time for the burn, and the cost of engaging with the community. Ideally, we will also include any negative impacts from the smoke, and if there are any escapes, we should include the impacts of those escape burns as an average cost per year. If we are mitigating for cyclones by increasing the wind uplift resistance of an existing house, we will include the cost of any assessments of the structure, the materials, products and labor needed for any upgrades, and the cost of any maintenance necessary. Okay, now back to our floods example. We had average annual benefits of option A, $908,050, and the cost of rebuilding the dam, $5 million. At this point, it does not make sense to compare the average annual benefits of option A with the cost of option A. If we did that, we will be comparing apples with bananas, because these two numbers are not expressing the same thing. The cost of option A corresponds to the total amount of money needed to build the dam, so it is expressed as a total, whereas the benefits are expressed in average annual benefits, which correspond to the amount of losses that will be avoided every year after the dam is built. An annual figure cannot be compared with a total figure, so we need to convert it all to annuals or totals. Also, the cost might be spread over a few years, but the benefits only start to appear when the costs have already been spent and may continue for long periods of time. So the cost and the benefits are not happening at the same points in time, and we can only compare amounts that occur at the same time. Finally, we haven't taken into account the maintenance cost per year, which are $35,000. So we need to do that too. To be able to produce a summary measure of the net benefits of a mitigation option, all values need to be converted to values at a common point in time. Usually, we convert them to the present. In a benefit cost analysis, we first have a look at the annual amounts of the costs, the annual amounts of the benefits, and how they spread over time. And then we calculate the total benefits and total cost at a single point in time, usually the present. I'll show you in a minute how we do all this, step by step, and it will all become much clearer. Okay, so let's say that the construction of the dam, option A, in our flood example, will take 3 years to be completed, and the cost will spread over the 3 years as follows. Year 1, $2.5 million. Year 2, $2 million. Year 3, $500,000. After that, we have maintenance cost of $35,000 per year. We're going to assume that the benefits of option A are realized after the completion of the dam, so from year 4 on. Just remember that depending on the project you are evaluating and how it is carried out, this could be different. Maybe after the first part of the dam is built, it will already provide protection to the catchment for up to a 1 in 20 or a 1 in 50 years flood. In that case, we will estimate the benefits of that and assign them to year 1 and year 2. But we're going to keep our example simple and have the benefits from year 1 to year 3 be equal to 0 and equal to $908,050 from year 4 on. For option B, it will also take 3 years to complete the creek upgrades, and the costs are spread as follows. Year 1, $1 million. Year 2, $600,000. Year 3, $200,000. After that, we have maintenance cost of $5,000 per year. The benefits of option B, $737,900, are also realized after the completion of the creek upgrades, so the benefits only start from year 4 on. Now, how many years do we look at the cost and benefits? In other words, what is the time frame for the analysis? This doesn't have a straight and simple answer. For our example, we could choose different time frames that could be justified. In theory, the time frame should be the length of time that maximizes the estimated economic efficiency of the project, after which we should consider a replacement for the project. In practice, the time frame usually extends through the useful life of the project or its most long-lived alternative. We could also choose a time frame at some point in the future when meaningful estimates of the effects of mitigation are no longer possible. So there is no rule of thumb that says, for this type of mitigation option, we should use this time frame for the analysis. We have to choose a time frame that is sensible for the mitigation option we are evaluating, and look at different time frames if necessary. For our mitigation options, the dam and the creek upgrades, we could be looking at a time frame of 30 years. Usually, for major new capital expenditure projects, it is recommended to use a practical asset life of 20 to 30 years, sometimes more. Usually 30 years for road initiatives, except bridges, and 50 years for rail initiatives. So let's have a look at the cost and benefits of option A and option B in our example over the course of 30 years. These are the costs year to year for each option. And these are the benefits year to year for each option. Now, the values that we have for cost and benefits in year 5 are not comparable to the values that we have in year 15. We need to bring them all to a common point in time. We will bring them all to the present. To do that, we have to decide at which rate the values change between now and a point in the future. This rate is called the discount rate. The need to discount a future cash flow can be viewed from two perspectives. One is that individuals prefer $1 today to $1 in the future, and another is that there is an opportunity cost of capital for investment. The fact that individuals prefer $1 today to $1 in the future is called the social rate of time preference, which is a rough indicator of how society values money now versus money in the future. For example, if I ask someone, what would you prefer, $100 now or $105 in 1 year? The person might say that they prefer $100 now. But if I ask the same person if they would prefer $100 now or $110 in 1 year, they might then choose the $110 in 1 year. If that's the case, then the rate of time preference is 10%, meaning that 10% is the rate that makes the individual indifferent between an amount of money today and an amount of money in the future. People usually prefer to consume now or to receive money now rather than later. Because of this preference, individuals might have a bias in favor of projects that produce benefits sooner rather than far into the future. The problem here is that this rate of time preference is very subjective, and it is likely to change from one individual to another. So deciding on a rate for all of society becomes quite difficult. The second perspective is that there is an opportunity cost of capital for investment, which corresponds to the return that will be received if that money was invested in something else. In the private sector, for example, in a business or in the bond market. The problem here, to estimate the discount rate, is that it is very hard to know how much that capital could have earned if it was invested in something else. So how do we choose the appropriate discount rate? There is no simple rule for choosing a discount rate. The best thing to do to set a discount rate is to follow the recommendations of the Office of Best Practice Regulation, that is part of the Australian Department of the Prime Minister and Cabinet. The Office of Best Practice Regulation suggests the use of a discount rate of 7%, although they also accept a rate of 8%, and suggests conducting sensitivity analysis with a 3% and a 10% discount rates. Since 2018, however, this has been subject to debate, and a recent report recommended that the Australian government adopt a 4% discount rate for infrastructure projects, because the current 7% rate is too high given the historically low levels of interest rates, and it might be an obstacle to invest in specific projects. But really, why does it matter so much which discount rate we choose? As we go through a numerical example, you will see why. In a nutshell, the discount rate we choose has a substantial impact on the results. Before we go back to our numerical example, one more important thing. What about inflation? And how do we include the Consumer Price Index, or CPI, in all of this? Inflation is another reason that a dollar in the future is worth less than a dollar today. When prices rise, we will be able to buy less things with a dollar in the future. When we conduct a benefit cost analysis, we have the choice of including future cash flows in one of two ways. We can include them in terms of their actual monetary value at the future date, which we call the nominal value, and accounts for CPI, or in terms of the constant dollar values, which we call the real value. In any case, all cash flows need to be converted to current dollar terms to be comparable in a benefit cost analysis. So if the analysis is presented in nominal prices, the discount rate should be adjusted for inflation. Because we usually estimate a given amount for average annual benefits and keep the same amount for all years, we're using constant dollar values. So it is easier to adopt the second approach. That is, including all future cash flows in terms of the constant dollar values and not worry about inflation. This is the standard practice in benefit cost analysis. And when it comes to mitigation of natural hazards, it is very rare to see an analysis that includes inflation. However, if there are good reasons to think that some cost on benefit streams will not follow general price increases, or if we think that inflation in the future is going to deviate significantly from a low and relatively constant rate, or if we think that it is going to affect how mitigation activities are carried out, then we might need to think a bit more about how to incorporate inflation in the analysis. Now, let's convert all of our values to the present. For the moment, we will use a discount rate of 7% and do sensitivity analysis on 3 and 10%. To bring all values of future costs and benefits to the present, we use the following formula for each value. We divide the amount by 1 plus the discount rate at the power of whichever year the amount is taken from. If we take an amount from year 4 in the future, this will be at the power of 4. If we take an amount from year 16 in the future, this will be at the power of 16. Now let's calculate the present value of all the amounts we have for the cost and for the benefits of both options for 30 years. The discounted present value of future cost year by year for each option are as follows. And the discounted present value of future benefits year by year for each option are. Now we make the sum of the discounted present values because all values have been converted to a common point in time. and are now comparable with each other. Now we can compare the totals. So the discounted present value of future cost for option A is $4,833,940, and for option B is $1,670,826. And the discounted present value of future benefits for option A is $8,885,020, and for option B is $7,220,149. Now, we're not going to do a full sensitivity analysis yet, but I do want to show you how the present value of cost and benefits change with different discount rates, so that you can get an idea of how much the discount rate can affect the results of our analysis. Observe what happens in this table. To all values as the discount rate increases, they all decrease. This means that the higher the discount rate, the lower the present value of a future stream of cash flows. So depending on the mitigation options we're looking at, the discount rate selected can make all the difference between a mitigation generating net benefits or not. Okay, that is it for this video. In the next video, we will look at the different criteria that can be used in a benefit cost analysis for ranking mitigation options and select the option or options that provide the best value for money to society.